Today we'll be talking about pH and pOH. So let's just do a quick little reminder from when we did equilibrium. Let's write the K expression for this equation. So if water and water interact, so basically you just have a bunch of water, you have these water molecules that are going to interact with each other, and they're in equilibrium with constantly exchanging protons. So you're going to have your hydronium and your hydroxide ions, that they're constantly changing back and forth. So remember the K, the subscript that we put in can change. This is going to be KW. As a side note, this is the water dissociation. I'm not sure if I spelled that right. Oh well. Constant. Okay, we take the products, those go up top. It's the concentration of H3O plus times the concentration of OH minus. And we don't use, on bottom would be the reactants. However you look at the reactants, they're liquids. Remember, we don't use those in our equilibrium expressions. So we have, this is our equation. Now, if you take a series of different things and you take the pH of it and you take the pOH of it, you will find that KW is always going to equal 1.0 times 10 to the negative 14th. Always. Yay. Okay, because of this fantastic constant, we can use it for determining things like pH and pOH. All right, if you do a bunch of calculations, let's think about something that is acidic. So something that's acidic, we will find that you are always going to have more of a concentration of, let's see, if I'm looking at H3O plus and OH minus, if it's more acidic, which do you think you'll have more of? Well, think back to when we did acids and bases. Which one did we define as an acid? That would be those H pluses, those protons, or the hydronium. So we're going to have more H3O plus than our OH minus, right? Because OH minus is what a base, we defined a base as. Acidic's going to have more of those protons. So similarly, base is going to have more OH minus than the concentration of our hydronium. All right. So you know that you can have something acidic, you can have something that's basic. Here, let's change that actually to basic. If something is neutral, you're going to find that the concentration of H3O plus is going to be equal to the concentration of your OH minus, right? You have just as much things that are acidic in your solution as you do basic, and so they neutralize each other out. We talked about this before. You're going to have just as much hydronium as you do hydroxide. Okay, so, and just as a reminder, remember this concentration is going to be more acidic. We don't need to write this out. We've got it. The H3O plus is going to be, when you have more of that, it's more acidic, more OH minus with the basic. We've covered that here. Okay, so in general, when we talk about pH and pOH, it's using those concentrations. So to calculate a pH and pOH, and these are things that you should have learned in your physical chemistry class, but I'm just recovering them. because I know that was a couple years ago. So pH is going to be equal to the negative log of the concentration of your H3O plus. And then your pOH is equal to the negative log of your OH minus. So pOH is in reference to your bases, pH is in reference typically to how acidic something is. All right, so let's just do a couple examples under here. So example, if I ask you to calculate the pH of a solution with these hydronium concentrations. Hydronium concentrations. All right, so for this, we're just going to do a couple examples. So the first one is 1 times 10 to the negative 12. And I will tell you, we define pH and pOH this way because if you look at concentrations, oftentimes we have them like this, where it's 1 times 10 to the negative 12 molar. Well, you know what? In chemistry, in general, whenever we can come up with a way that's more simplistic, we do. So instead of writing a bunch of things with negative exponents, it's so much easier to, if I were to find the pH of this, so we said that pH is going to be equal to the negative log of that concentration, so 1 times 10 to the negative 12. Our pH is now just going to be 12. Now, isn't that a much easier number to work with? So that's why we came up with it. So here's just another quick example. If we have 0.0009 molar, which is the same thing as if I were to move this over 1, 2, 3, 4. If I were to put this in scientific notation, it'd be 9 times 10 to the, 1, 2, 3, 4, to the negative 4 molar, right? Those are the same thing. If I were to get the pH of this, remember it's the negative log of that number, so I'm going to put 9 times 10 to the negative 4. We end up with a pH of 3.05. So again, much easier numbers to work with. So that's basically why we use pH and pOH. It's a lovely way to kind of set things up to help ourselves out. So let's just go over a quick thing for the pH scale, so that way you have an idea of what's out there and what you are typically using. So if I'm going from here over to here. Okay, so on this side, we're going to put 0 over here. We're going to put 14 up here, right here in the middle. We've got 7. And let's see if I can't get a nice scale going. Let's see, halfway between 7. I don't know. Okay. I didn't really make this as pretty as I was hoping to. Okay, 6, 5, 4, 3, 2, 1. Well, that wasn't too bad. All right. So this is going to be 1, 2, 3, 4, 5, and 6. Then we got 1, 2, or 8, 9, 10, 11. Uh-oh, didn't do as well on this side. Oh well, close enough. All right, so here's my scale. Now, if I'm looking at this scale, on this left side, this is going to be very acidic over here. Anything that's a small pH is very acidic. Anything with a very large pH, so over on the 14 side, is very basic. So let's go through it. Oh, and then right here in the middle, this is neutral. Let's go over a few examples of what might be some things that will be classified in here. So in this section here, so between 0 and 2, you have things like battery acid, your stomach acid, that's why it's able to break things down so well. And then vinegar is also in here, in that section. All right, so then between 2 and 4, We've got things like acid rain, which I'm sure you have seen the effects on buildings and such, either in pictures or if you're lucky enough to do a lot of traveling around yourself, if you had that pointed out to you. Soda is actually quite acidic, and that has to do with the CO2 in it. And actually many juices are qualified, or have a pH between 2 and 4. Okay, between 4 and 6, here we have things like tea, which I would like some of that right now. Maybe I'll have to do that here soon. Some coffee, which I'm sure many of you absolutely love. And you're going to think this is kind of funny, but your own sweat. Your own sweat is actually acidic. All right, between 7 and 8, so kind of our neutral zone, we have pure water is in here. Urine is actually pretty neutral, along with milk and tears and blood. So this is a lot of things that come specifically from a body, right? These are fairly neutral things. This is typically what our body likes for a lot of different things, unless it's a given environment where it wants something specific, such as your sweat or your stomach acid. All right. And then just a little bit more basic, between 8 and 9, we have things like seawater is actually a little bit basic. Let's see, baking soda, which is why we use baking soda as a neutralizer for acids so much, as it's slightly basic, which is super handy. And then in here, we also have deodorant. All right, I think I spelled that right. Who knows? All right, so if you think about where sweat is, we've got sweat over here. So deodorant's just slightly basic to offset that. So that's actually the whole point of deodorant, is it helps combat the sweat via a pH thing. So that's kind of neat. All right, between 10 and 12, here let's stick with the colors I've been doing. pH of 10 and 12, you have a lot of cleaners. So you have things like soap and shampoo, toothpaste. And then as you get even more along that line, so more basic, you have things like hair remover. It is actually quite basic. So basic things are pretty good at removing and kind of hurting us. I know everyone talks about, oh, things that are acidic. Things that are acidic are scary. But really basic things are actually really scary too. So just keep that in mind. All right, between 12 and 14, so these are the kind of scarier things as far as hurting yourself goes. Bleach, which the bleach we use is at a very, very small percentage, which is why it doesn't really hurt you. All right, so we've got bleach and then detergents. And again, these are all very small concentrations, which does affect the effect on you quite a bit. Now, higher concentration thing that is pretty scary is an oven cleaner. So definitely, if you ever clean an oven, use really thick, awesome rubber gloves. And then drain cleaner is also in this higher pH range that's very basic. So that's the general gist of our pH scale. All right, let's just do a quick reminder, because pH is dealing with a lot of logs. So reminder that if I have log of y equals x, this is the same thing as saying 10, because if I don't have anything written down in this base section here, we assume it's 10. Okay, so remember, you take what's in the base, it's going to go in the base here. Here, actually, let's just make this all color coordinated, make things easier. All right, so it's going to be 10 raised to, this is our exponent here, this x is our exponent, so it's going to go up here, equals our y. So this is how you rewrite it. So this is just a reminder of how logs work. So based on that, let's apparently do a review of everything we've done so far. All right, let's rewrite pH and pOH equations in exponent form. Because you're not always going to be told the concentration, you might instead be told the pH or the pOH, and you should be able to then find the concentration. So if I were to rewrite it in exponent form, I would have 10 raised to the negative pH equals our H3O plus concentration. And then we also have 10 raised to the negative pOH equals the concentration of our OH minus. Okay, so we have all these relationships. So let's actually put together a diagram on how all of these things can be found and how they're related to one another. So in one corner, I'm just gonna scroll up here. We're gonna have a big old diagram that I'm gonna put together here. Why won't it let me scroll? Ugh, whatever. All right, so we've got our H3O plus, concentration of our H3O plus in this corner, concentration of our OH minus in this corner. And then if I draw down here, I've got the concentration, oh, I'm sorry, not concentration. I've got my pOH, and over here I've got my pH. So let's see how these all relate to one another in one big thing. So remember at the very beginning we found the KW. So let's try a different color here. KW we said equals the concentration of H3O plus times the concentration of OH minus. All right, and we said KW is always 1.0 times 10 to the negative 14 equals our concentration of H3O plus times our concentration of our hydroxide. All right, so this will allow us to either calculate our H3O plus if we're given the concentration of OH minus, or it'll allow us to find the concentration of our OH minus if we're told the concentration of our H3O plus. So we've got that relationship going for us. If instead I want to find the concentration of something and I'm given a pH, so I'm going from pH up to concentration of our H3O plus, I can then take your concentration of H3O plus, remember, equals our 10 raised to the negative pH. If instead I'm going from H3O plus down to pH, well, we have the equation pH equals our negative log of our concentration of H3O plus. Similarly, over here, if I'm going down from concentration, I have the concentration of OH minus and I want to find my pOH, I can do the equation of pOH equals, I don't know if I'll have room here, I'll just put it on the next line, negative log of the concentration of OH minus, our hydroxide ion. All right, and then going the other way, going from pOH to a concentration of pH, we know that we have the concentration of OH minus is equal to 10 raised to the negative pOH. Okay, and then we just have one last section here going from pH and pOH. So, let's see, we'll do it green, why not? We know that pH plus pOH always equals 14. So if we know our pH, we can plug it in. If we know our pOH, we can plug it in, and we can get either one from that. Now let's break this down. How do I know that pH plus pOH equals 14. We'll take a look at our Kw equation that we have up top. We have the 1.0 times 10 to the negative 14 equals our concentration of H3O plus, our hydronium, times our hydroxide's concentration. All right, so, well, actually here, let's not start with that. There's a couple ways we can derive this. Let's just start with our known that we have here. So I told you that pH plus pOH equals 14. Let's plug in a few known things for it. So we know that pH is the same thing as pH is equal to the negative log of the concentration of H3O plus. And then we know that the pOH is defined as negative log of OH minus. And we said this equals 14. I'm just substituting in our pH and pOH equations into this. All right, going from here, I can combine these two logs based on our logs. Remember, whenever you add something together and they're both logs, that's the same thing as multiplying them. So first I can pull my negative out, so it becomes negative log H3O plus our log, because I pulled the negative out in front, I can just have this whole thing equals 14. So now I know that the negative log, if they're added together, is the same thing as them multiplying when I combine them, of concentration of H3O plus times OH minus is going to equal 14. Now, let's take a look up here. I have that equation exactly. I have H3O plus OH minus, so we can substitute the 1.0 times 10 to the negative 14 in. So I can now say that my negative log is equal to our 1.0 times 10 to the negative 14 equals 14. Oops, I forgot the 1 in there. Somehow it didn't write. Okay, so, which we know to be true, right? This is true. Checked. Good. All right, so that's how I got that it equals 14. Is that pH plus pOH, we can plug in the known that pH and pOH, their definition is equal to the negative logs of their given concentration. I can then combine them. We know based on the Kw that those multiplied by each other equal to 1 times 10 to the negative 14th, which equals 14. All right, so using this box that we have here, we can go and find any of these bits. If I ask you for the pOH of something and I give you the concentration of H3O plus, you should be able to find me a pH by going down this way, and then find me the pOH by going this way. An alternative is you can find me the OH minus from this using this equation here, moving over to an OH minus, and then we know how to find our pOH from there. We can go down that way. So we got multiple opportunities for going through this. I don't really care which way you go. You have multiple ways you can go about it, but that's how you use this lovely square that I put together. So let's just do a quick practice together, and then I will set you free to do some on your own. So let's do an example. Okay, calculate the pH, the OH concentration, the OH minus concentration, the hydroxide, and the pOH of a solution of 1 times 10 to the negative 4 molar HCl. Okay, so the first thing that I could do here is if I'm looking for the pH, this is HCl. HCl is an acid. So that means that I have the concentration of an acid. So I've got 1 times 10 to the negative 4 molar, I said, is equal to the concentration of our HCl. Because it's an acid, it's going to dissociate and form, remember it's a 1-to-1, if using our stoichiometry, it's going to be equal to the concentration of our hydronium ion. Because there's only one hydrogen here, right? It's just going to be 1-to-1. Okay, so to find the pH, remember pH is just equal to the negative log of the hydronium ion's concentration, which we now have, so we can plug that in. We got negative log of 1 times 10 to the negative 4 molar. We don't need to worry about the units here. Woohoo! Plugging that into your calculator, you're going to end up with a pH equal to 4. All right, that's one of our questions answered. Yay, check. Okay, we want to find the concentration of OH minus. OH minus's concentration, we can find via a couple different ways, right? So right now, what we know is if we look up here, we've got our pH, we know our H3O plus, we can find our OH minus using that 1 times 10 to the negative 14. Okay, so OH minus, well, I guess we don't know what it equals, so let's reset this up. We know that OH times our H3O plus is going to equal 1.0 times 10 to the negative 14. Well, we are given the concentration of our hydronium ion, so we can plug that in and we're left with just one thing. So first let's isolate our variable we're interested in. So we do that by dividing by our hydronium ion. That cancels out. So then we know that our OH minus is going to be equal to 1.0 times 10 to the negative 14 over, let's plug in our concentration. That was given to us as 1 times 10 to the negative 4. Okay, plugging that into your calculator, you get a concentration of OH minus equal to 1 times 10 to the negative 10. Now, we're not done here. pH and pOH are unitless, so we don't need to worry about units there. However, concentrations are not. Think about what units you need for concentration. Concentration, we have always been using units of molarity. So you have that big M. That's going to be your concentration of OH minus. All right, the last thing on our list, so we did the OH minus, check. Last thing is our pOH. So our pOH, remember our pH plus our pOH equals 14. We found our pH to be 4, so we can say 4 plus our pOH equals 14. So we just subtract down our 4. We find the pOH is equal to 10. Guess what? There's multiple ways you can go about this. Another way you can do this is or. We found everything, but in case you wanted to know another way you could do this, if you remember, looking back up here, we've got OH minus. If I want pOH, let's look back up at our square. If I want pOH and I'm looking and I have OH minus, I can take the negative log of that concentration to find our pOH. So pOH equals our negative log of our 1 times 10 to the negative 10, which is still equal to 10. Woohoo! It's the same thing. So you can go multiple ways about this. It doesn't really matter which way you go as long as you are still following correct rules of math. Okay, so that's generic finding pOH, pH, concentrations of your hydronium ion and concentrations of your OH ion. Oh, I do want to go back up here. Let's go back up here really quickly. H3O plus, remember, is the same thing as your concentration of, why won't it let me write? There it goes. Concentration of your H plus. Okay, those are the same. You'll be given different things depending on who's giving it to you. So I just want to make sure that you are aware that the concentration of your protons, your H plus, is the same thing as your concentration as your hydronium ions. Okay, let's talk about buffers, and then you can go off and do some practice problems yourselves. So a buffer is a solution that resists the change in pH. All right, so basically what this is going to be is it's going to be a weak acid and its conjugate base. So let's talk about an example here. So an example of this would be NaC2H3O2. This we know would break up into ions that are Na plus and C2H3O2 minus. Okay, so if I were to take an acid, so if I just have some sort of H plus acid, and it's going to react, it would react with our floating around. So we have this molecule that we put in. However, when we put it into a solution, it'll break up into these ions. So what this H plus wants to react with is going to be our, the more basic one, right? The one that actually has a charge that could balance it out. And this will end up forming HC2H3O2. So if you take a look here, here's our acid. This is acting like a base. This is our conjugate base, right? Because if we label this over here, this would be the conjugate base. And then, so we put this in, the conjugate base is what's going to be reacting. This is going to be dissolved and not interacting with anything. It's just going to be like a spectator ion, if you recall that. Now, I have this newly formed acid over here on the right side, but it's been neutralized essentially to some extent. So, alternatively, this HC2H3O2 will be flying around, and if it comes across something basic, it will form water and this ion again. Okay, so if you look at this, it kind of is going to be a cyclical thing. Anytime it comes across an H plus, those ions that form will make this lovely molecule, so that way the ions can't be floating around to make it acidic. If that molecule comes across an OH minus, our hydroxide, to make it basic, it'll form water and that ion again, which can then interact with an H plus. So a buffer is something that allows us to work with something and it's not going to let the pH change much one way or the other. So if you work in biology, this is something super handy. When I was doing a lot of work with bacteria, I used buffers all the time because I wanted my bacteria at a specific pH so that way they don't die. But I needed to be able to change certain things to my solutions, but I didn't want my bacteria to die based on the pH changes these additions might make. So I would put in a buffer so that way the pH doesn't change dramatically, more basic or acidic, which might be a problem for my bacteria. So same will be true for a lot of people and things. So there's a lot of stuff that we use buffers for. Anyway, so that's the general gist for pH and pOH and calculating all of the above and concentrations of hydronium ions and hydroxide ions. Biggest take home here is going to be this box up here. This is going to be your best friend when it comes to calculations for pH, pOH, concentration of OH minus and H3O plus. So this is something that you should be able to make yourself. This is something that I do recommend working on memorizing for, just being able to pull it out on a test or what have you. All right, well, I hope that makes you feel better about calculations of what pH, pOH, what it all means, etc.